see. You guys love math so much. I'm joking. You guys love math so much. You're here for the lunchtime talk, which is great. I hope to see you guys in the next few weeks as well. There is food at the end. Sina has promised pizza. Cool. So I'll start this semester's talk series off. I'll be talking about mathematical modeling of infectious pathogens, the how and the why. Okay, so I did a Bachelor of Science. I majored in mathematics and immunobiology. If you guys get the chance, I highly recommend majoring in two things. That way, like if you want to do applied maths now or later, you have a better perspective of getting into it. But having said that, I know friends who did pure maths and then later on went into applied as well. So 2020 I did honors in applied maths. I had a look at some disease modeling. That was when COVID hit, and actually at the start of 2020 I was thinking of modeling influenza spread. That was like the biggest thing in Australia before COVID hit. And then what I ended up doing was I tweaked the model a little bit, and I had a look at two different disease spread types. So I'll talk about that a little bit further down the track. You guys have heard all the news on COVID. So some of these keywords you guys have heard of before. And if it's completely new, if I'm going a bit too fast, feel free to ask me during the talk or at the end during the question time. So last year I started a PhD, and I'm doing that in science. So it is actually based in the vet school. It's on the other side of the campus. And I'm actually doing the disease modeling for them. So it's cool that I'm able to use the two majors from my undergrad and actually use that in one combined project. So today I just want to talk for infectious diseases, give you guys like a very brief overview, so much detail there, but also like how we build the models and why we build the models, okay? You guys, again, might have heard the news. That was all over the news, and there's a lot of models after March 2020, okay, when people started to understand the biology a little bit. In the first 1 month, they started to use those data, and then they figured that into models. Okay, so as we got more biological data, then the models became more detailed and more closer to as accurate as we can get. So yeah, I'm just going to give you guys like a brief rundown on some infectious diseases. You guys have heard of COVID a lot, so I'll try to avoid that in some parts. Okay, so foot and mouth disease, you guys might have heard of that, especially if you've done a little bit of traveling to Bali or Indonesia. So that's actually picked up in soil, and if it infects an animal herd, let's say if cows or goats are infected, it's actually really bad and it spreads really quickly. You actually have to end up killing the whole herd. Okay, so that's super serious. Cholera, so that's in contaminated water, supply contaminated food. Malaria, so that's spread by mosquitoes. We don't really have those cases in Australia, but we have a lot overseas. And ringworm, so ringworm is actually the disease, not the pathogen. Okay, so I've put the first 3 slides in infectious diseases, and then the next slide is the pathogen responsible. So before we jump into modeling any disease, you need to first understand what pathogen is causing that disease, or else you might have some incorrect assumptions when you set the model up. Okay, so foot and mouth disease, that's very creative name. Foot and mouth disease is a virus. For cholera, we have the Vibrio cholerae. That's a bacteria. For malaria, there's actually Plasmodium falciparum. That's a parasite. And then for ringworm, that's actually caused by over 40 species of fungi. Okay, so that's a pathogen. And then the next slide is how do they spread. For these 3 slides, you really need to understand these 3 components of your disease before you jump into a model. So foot and mouth disease, it's spread via direct contact with contaminated skin or surfaces. With cholera, that's contaminated water and food supply. Malaria, that's mainly the Anopheles mosquito. There's actually several species of mosquitoes. 8x, QX, phenolphthalees, just to name a few. And so some people have been really worried about malaria when their region doesn't have any anopheles mosquitoes, right? So yeah, what should we pay attention to? What should we factor in? And then ringworm, it's spread by a direct contact with skin contact. So it might be people to people, might be people to pets, might be people and contaminated surfaces, right? So if you just think about that in the context of COVID, right? You guys have heard of a lot of the models and also prevention and reduction measures. So home quarantine isolation is a huge way to reduce cases. Okay, if we have a look at foot and mouth, or actually let's look at cholera, contaminated water and food supply. Okay, so if we didn't understand this thing so much and we could see that, okay, cholera is spreading really quickly in the population, we're going to do home quarantine. Okay, water supply is still going, would that stop the spread? Okay, no. Okay, so understanding the spread method is actually really important. Okay, so what is a model? I found this image. This is actually a Lego product of the Opera House. Okay, so models are usually a lot smaller in scale. They're not the true thing. Okay, and is it useful to create a model? Okay, so a lot of experts have debated this topic, and so we're going to have a look at the components of the model, how they're used, and then at the end of the talk, maybe you have your own opinion. All right, so in this, like if you want to go to Opera House to watch a concert, well, this is not what you want to approach, right? But with the model, you can actually examine certain characteristics and understand the key features of what you're looking at. So COVID-19 models, I have gravitated back to this. There was a lot of important studies, mainly published in March and April in 2020. Okay, so first few cases, it was detected in December, and then the first few cases in Australia was detected mid-January 2020. Okay, and then roughly 1 to 2 month period was to understand the biology of it, how quickly it spread, how contagious it was, how it spread, and how we can control it. And so there was actually a few large studies. I've just highlighted 2 here. All right, so you guys might have heard of the modeling, transmission, and control of COVID-19 pandemic in Australia. This was actually created by a team in the University of Sydney. You guys might have heard of that on the ABC News. So this was actually a huge model, and actually the results of this was published in Nature later on. Okay. There was also another large paper published by the Imperial College of London. And so they were working closely with the WHO. They had a look at some intervention methods to reduce the spread of COVID. So those 2 are some of the bigger papers. There's a lot of the other bigger papers, and then there's papers commenting on these papers to improve or fill in the gaps that they might have missed. Okay, so this is actually the ABC News article that summarized the paper findings. Okay, so a paper can be hard to read. Who has read a paper of any nature or skimmed one? A few show of hands. Cool. So papers can be really dense to read, and if it's really important and it concerns the public health, then ABC News or different outlets might summarize the key findings. Okay. So in the title, if you just read that, you basically have the crux of the paper. So it can be controlled. The spread of coronavirus can be controlled if 8 out of 10 people stayed at home. Okay. And then if you go into some of the main points highlighted in that news article, first 2 points mainly say that again, okay, but it also highlights that, well, if it bumps down to 7 out of 10 people, then the idea of flattening the curve is lost, okay. There is like a period where it fluctuates and then it will still skyrocket again. Okay, and then the third point is really interesting because school closures was a big thing. They closed schools, they closed work. There was certain periods where they might close it for a few days or a few weeks at a time. And so what this paper actually found was that school closures didn't really have an impact on the peak level. But what it did do is that it pushed the peak out. And so this is one of the graphs that showed that if it was 70% of the people that complied with the guidelines, it does have like a little bump and then decrease, and then it shoots up again. There's the 80% compliance, and then 90% compliance, it drops down.
So, do you have a question?
Yep.
People's, like early on COVID, people's, well, the scientific community, it's not your models. Do you ever question the fact that it was used to justify all this during the COVID pandemic? Like you're saying, like the curve, nothing that we tried really did flatten the curve.
Right. Yeah, so yeah, that's a good point. Is the model even doing anything useful, right? Just so I understand your question properly, is saying like, since the model was created like earlier on, there was a lot of missing gaps. Sorry, can you say that again?
Did you ever question, it was quite unusual that we relied so much on models early on, and we still rely on models even though they were all pretty inaccurate.
Yeah.
Like
yeah,
we still rely
right.
on COVID, not the same COVID models we did at the pandemic, and they haven't really
done much. And then slowly slowly the state was just saying, oh yeah, let's just forget about quarantine and then let it ripple through. And so was this useful, right, in the early stages? In the early stages, I think like when this model was published, there was a lot unknown. So it was kind of like them grasping on the pieces that was there. And so like it doesn't really show, maybe like you'd say, well, 75%, would that be a better like indication? Or if we like detail, then we might say, oh, maybe it's 76%. Like, does that detail actually matter? And on population level, like it's hard to track that. And so they give like really rough numbers. Yeah. So I think like, even though it's wrong here, the fact that they were able to say this started filling in some of the gaps that were not known. Did that answer your question? Right, so if we look at school closures, that's the SC. SC is in the green. So NI is no intervention. CI, we've got isolation, case isolation, and home quarantine. And then green is putting them all together with school closure. And so the main thing I want to point out is that the school closure didn't really flatten that peak, it just pushed that out. And that's because you don't have as big of a susceptible group to infect at once. But then as school closure, like it's not going to be forever, right? Once you close that, then you've got your susceptible, and then they would still become infected. So this was an important finding of the study, and they were like, okay, actually, maybe we should do so many school closures and over a long period. Exponential growth of cases. Okay, so I'll just highlight this briefly. It was put in the ABC news article. So if you have a look at this diagram on the left, so you've got one infected case, and then if one infected case causes 3 other cases, and then from there, it looks like each case is causing 2 to 3 new cases, and you can see how it just ripples out in the exponential spread. Okay, but then if we look at home quarantine, case isolation, then the red lines are actually the infected new cases, and then the gray was like what it could have been before, but now that's being reduced. So you could see that home quarantine has an effect there. Case isolation. All right, so I'm going to go through mathematical models. I gave you guys like a biology slide. I think most of you guys are probably maths majors here. So I'll head into the maths part of this. So SIR models, you can really break it down into 3 parts. And so S is the susceptible individuals, and so they can catch the disease. I is then the infected individuals. They've got the pathogen inside them, and then R is the recovered. So sometimes we call R the recovered, or we say R is the removed. If they died, and we say they're removed. Okay. And beta P is actually the force of infection P. We've got the infection rate, so how quickly are the susceptible individuals becoming infected, and then here we've got the gamma, which is the people who are infected, how quickly do they recover. So COVID, it was around 12 days or so, and then public health, like the news, they kind of just bumped that up to 2 weeks. That was just easier to communicate. So the first SIR model was actually constructed in the early 20th century, and it was mainly looking, there's two guys, Kermack and McKendrick. They were looking at the Bombay plague epidemic. And so a lot of people were just dying, and then they reported the death cases, which are actually the black dots here. And then they said, oh, actually, like the peak here, like can we model that to explain how this dynamic occurs? And so they actually put the SIR model together to explain those death cases. And so if we have a look at the three differential equations here, this is actually the rate of the susceptible. And here we've got minus, okay, so we're considering a closed population. There's no births, there's no introduction of new susceptibles. It's just a minus because those susceptible will become infected, and we'll say that, well, with the Bombay plague, they will die off, so they don't recover and become susceptible again. Okay, so this is just a minus. And we've got the beta, and we're timesing S and I together. Okay, so this is actually the proportion of the susceptibles in the population times the infected. So to become infected, right, a susceptible will have to come in contact with an infected. And so if your infected individual proportion is 0, well then there's no one's going to be becoming infected, right? So that will drop down to 0. So that part then bumps into the infected, so this beta SI term, you can see it down here. And then from the infected individuals, you then you take out those who recover. So you minus gamma times the proportion of those infected. And so that term gets bumped in here. Okay? R can be recovered or removed. Because it's a closed population, we say that susceptible plus individual infected plus recovered, that would be n. So if we're looking at proportions, n would be 1. Okay, if we're looking at the number of people in each group, then n would be the population. Okay, so it depends on how we're constructing this. So they actually found that the result of this matched very similar to the death cases. And so this wasn't used to forecast the peak. This was actually to explain that peak. Okay, so we're just going to have a look at the two main rates here, transmission rate and also the recovery rate or removal rate. SIR models are very simple, okay, and they can actually become very complicated, and I've got a few examples later on. So let's say beta is the transmission rate. So the higher beta is, the more people become infected. You guys might have heard of R as well, maybe. I'll go to that later on. So beta, what we're actually looking at is population mixing dynamics. So how closely is our population living together? Like if everyone's living spread out in rural areas on farms, then beta would be a lot lower compared to in the city when there's dense population groups. So we're looking at how contagious the disease itself is, just the pathogen. So how easy it is to actually hijack cells and then start replicating. And we're looking at how many people are susceptible. Okay, if everyone's vaccinated, they've got immunity, then well, beta wouldn't really be a thing, right? But yeah, that would change, and so beta is kind of like the average or the median of these, like all lumped together. So here we can look at age. Okay? The young and the old might be more susceptible. Immunity, so if there's immunocompromised individuals in your population. Vaccinations, if they've had a vaccination before or they were previously exposed. So COVID was new, okay, so that rippled through society. Influenza is kind of endemic, so that seasonal And so people might have vaccinations or pre-exposure before. Alright, so that's beta just looking at it as transmission rate. Sometimes this, if you look at models, they actually pull this out, and it's actually like a coefficient made up of a lot of parts, and then they define each one. They're based on those components. So in terms of population mixing, this is actually taken from my honors work. I was having a look at different mixing, day mixing and night mixing. So it might be that your population changes their network based on the day or night. Daytime, it might be that working individuals might travel far to different regions for work. But then let's assume that the young and old stay in their regions. So when you construct a model, you have a lot of assumptions. You try and capture the main parts, but sometimes you need to drop out certain features because it's just not feasible to put all parts in. Okay, so here I've color-coded blue as one region and green as another region. And so here we've got the working individuals between the regions mixing during the day. They can also mix between their own groups, and then the young individual and old can mix within their own group. Night mixing, we've got the young working and old mixing all together. Okay, so it might be that they're back home, it might be in shopping centers, parks, and so then there's more mixing there. Alright, R0, so I mentioned this before, how contagious is the disease? There's a lot of measures for this. R0 is a popular one, but R0 is not always used. R0 is actually the basic reproduction number where if one person's infected, and let's say you just plop them into a fully susceptible population, how many new cases would that infected case cause? Okay, so sometimes it's not appropriate to use R0 if like the population already has the disease. Okay, because then this is looking at a fully susceptible population. And so R0 was really murky when COVID started. Everyone was saying, well, maybe R0 was 2, maybe it was 6. It got up to like 8 or even 13 in some papers. And so when they were doing contact tracing back and they were saying, oh, okay, you were infected, how many people were in your network that were also infected, sometimes you just forget where you've been to, and who it might be that someone else in your network got infected, but then they didn't report it back. So that was really murky, and there was a huge spread for COVID in terms of the R0. And that's why even in the models, when they were using the R0s, when they came out of the studies, that also gave a mixture of the suggestions and impact. Okay, so we're going to look at types of models. I talked about SIR model. That's mainly how you break down your groups. And in terms of the types of models, we can mainly think of them in 2 groups, deterministic or stochastic. Okay? So deterministic, what we're looking at is when we run the model, no matter how many times we run it, we get a fixed result. Okay? And usually that's because, well, if you've got, let's think back to the SIR, 3 differential equations, you've got one solution there. Okay? So no matter how many times you run it, beta and gamma will be the same. That will give you the same output. Stochastic, that's based on distributions. Okay, so let's say you've got a range and you're looking at R0 maybe between 2 to 6, and you might have a distribution where you might say there's actually a lot. Or you might have a distribution where it's between R0 as like 4 or 5, and then you just run the model, and every time it runs, it will pick a different R0 value, or use it in the model and spit out its mapped out projection. And usually in stochastic models, you run it a lot of times, maybe 100, maybe 1,000 times, and you get like the average of those results. Okay, so deterministic models are usually fairly simple. They can be homogeneous, so the result will be the same, or heterogeneous. It can be heterogeneous if you break down your population with age. Okay, let's say 0 to 10 years, 10 to 11, depending on how detailed your model is, deterministic models can still be heterogeneous. They're rough approximations, and they usually require less computing power. So what I did for my honors project, I was having a look at large regions. I was basically trying to recreate a very simple version of ACE-mod. So that was the one used, that was the one constructed by City Uni to look at COVID spread. And they actually broke it down to blocks, like postcode, even smaller than postcode regions. And so I was looking at SA4 levels, statistical area level 4, and so there's around 28 of those areas in New South Wales. You can think of them as your LGAs. Okay, so yeah, deterministic model, that took me 6 seconds to run my model for the deterministic one, and then stochastic one took me a bit over an hour to run that. And so yeah, they're more detailed, they're usually more realistic because of that sampling. They require more computing power, okay, and they're heterogeneous, which is what happens in real life. It's random mixing. Okay. So Q fever. Okay. I didn't mention this in the 4 diseases at the start. Q fever is actually the disease I'm working on right now for my PhD. So I don't think a lot of you guys might have heard of Q fever at all. I've spoken to some people who have lived on farms. And if you've lived on farms in Queensland and New South Wales, you would have heard of Q fever. You would have had to get the vaccination. I was speaking to a staff member who grew up on a farm in Western Australia, and they've never heard of Q fever. So it's dependent on region, and it affects animals, but also it's zoonotic, which means that it can spill over from the animal population into the human population. It's actually caused by the pathogen Coxiella burnetii, bacteria. And they had a look at the model in this aspect. Okay, it's not an SIR. You see the component there, SIR. There's also an I minus. Okay, so they put an I minus here as exposed, okay, infected but not showing the disease. So asymptomatic and symptomatic. And it might be that they wanted to do this because those that were infected but not symptomatic, it might be that their shedding rate is a lot lower than those that are infected and symptomatic. So they've actually broken that down mainly to look at the different shedding rates. They've included an environmental bacterial load here. So they're actually looking at this shedding from the infected and then feeding that back into the rate that the susceptible groups are getting infected. They're also saying here in the model that infected but asymptomatic might be able to recover. Okay, so they can go back to a susceptible state. And so this arrow was not seen before the SIR basic diagram. There's also this part where if you're infected and symptomatic and you recover, they're saying, well, if you recover, you don't recover fully. You kind of recover that you don't shed. And so that R can also feed back into the infected. So there's the two loops going on here, and then there's this overall flow. There's also this exit here from the environmental bacterial load. So over a time period, then the bacteria will decay. Okay? It might decay naturally from the environment, or it might be cleaned out. So that's one variation. But there's another one. So this is also Q fever. So here they're looking at susceptible, and then A, that's asymptomatic. You can see, well, they've just renamed that instead of I minus, right? And so what you can do is you can actually call these boxes whatever letter you want, right? You can say like it's Q or W. Generally, you follow a convention, right? S is usually susceptible. If you want to be quirky, you could put S as recovered, as long as you define it properly in the model, right? They're just pronouns. And then V here is vaccinated, and then this part, they've added this part in, which the other model didn't. They're still looking at an environmental load, okay, and so it looks different here. There's 5 differential equations, whereas this one would have 4 differential equations, maybe 5 for the environment. Right, so that's a deterministic model here. And then this one is a stochastic. Alright, and then malaria transmission. So just as a step up, right, I just want you guys to see you can be really creative with constructing a model. Okay, how you look at your population. Before this was just S, and then infected was, they've already stepped it up, they've broken that into 2 groups. And here, they've actually broken infected into 4 groups. Okay, they've got asymptomatic and symptomatic. And it might be that the shedding routes are different. It might be that if you're symptomatic, you might start to show different behavior. You might not mix with the community as much. Okay, so that's maybe why they added that in. Okay, X and Y, we've got children and adults. So it might be that the biting is more frequent in children or adults, or that the behavior dynamic is slightly different. They factored that in. Okay, so it looks like there's a lot of the compartments, but really, if you think of the children and adults as the 2 main groups, and then within each group, you've got susceptible, then you've got asymptomatic, and then you've got infected. That is very similar to what we had here. Okay. Right, and then there's also vector population. So there's the malaria spread by mosquito. So if there were no mosquitoes, malaria would spread. Okay? So that's not aerosolized, that's not direct skin-to-skin contact. And so with malaria transmission, in terms of prevention or reduction measures, they're actually focusing this on reducing mosquito populations. So those were the 3 main models I wanted to highlight, mainly to show you guys how it can get complicated, but also there's a lot of space to add things in and be creative with it.
Is there no recovered population in the hospital?
There is no recovered. Good spotting. Okay, so depending on what the model is focusing on, okay, different models will have different parts. I think you suppress the, I'm not too sure about malaria, but it might be that you suppress the symptoms with the medication, but it might be that you still be infected chronically. Or it might be that if they want to model for half a year, 1 year period, and if recovery takes 3 or 4 years, they might cut that out of the model, okay? Because each bubble here will produce another differential equation, right? And so if you don't need it for your focus, you can drop that out.
Sorry, for the, I think it was your PhD on QV one.
Yep.
What is the Bayesian equation? Yeah, what does that mean?
Bayesian approach.
Yeah.
Right, Bayesian, so that's a statistical distribution. So basically you've got your distribution each time you sample through, so you might run the model and you might run it, each loop is for a day, and each day the mixing might be different. Okay, so the cow movements might be different, and so then the exposure might be different as well. And so some days you might get like a lot of cows infected, or other days you might not. And so a Bayesian here is the way that they sampled from the distribution. If there's any statisticians here, please correct me.
Also, what did you say the I minus and I plus were?
Right, yeah, so if I remember this correctly, I minus here is infected but asymptomatic. And I plus is that they're infected but they're symptomatic. And there's also, I think also that they're asymptomatic but they don't shed as much. Okay, so those were the 3 main models, and I just want to leave you guys with a final quote that not all models are accurate, but some are useful.
for usually for models, I was seeing a lot of differential equations, right?
Yeah.
Do you have models that are not basically differential equations? Like,
Yeah, so when I mentioned the two main model types,
yeah.
differential equations are usually deterministic. Yeah. And so if you're sampling from a distribution, that's usually stochastic.
So what kind of like models would you have?
Yeah.
Like what
so,
kind of formulas would you get with like a different
Right. That's really interesting. We probably don't really call them formulas.
Yeah,
We call them
equations.
rules. Yeah. And so you basically set up a program and you've got your parameters and you've got a loop, and that loop might be day mixing each day. And you run the model maybe for a year, and you're going to sort of see like each time you loop it during each day, you then sample from the distribution. We call those agent-based models or individual-based models.
So I would say you still define it with a differential equation, just rather than solving explicitly, you're sort of approximating a solution stepwise.
We think of them as the discrete.
Oh yeah.
Yeah, it'll be like discrete. I think we won't have like half a person infected. Yeah. So difference equations instead of differential equations. Yeah. If you guys are interested in this, I think the way that I got into this was taking math 3 888, but also math 3 888. You sort of start to put a biological system together with maths. So Martin teaches that, and then
Is that mathematical computing or?
mathematical computing might have a project on this.
Okay.
Yeah, but I don't think the most focus is on it. Cool. All right, we'll wrap it up then.